Welcome to today's session. We're diving into problem number 879, titled Profitable Schemes. This problem challenges us to explore dynamic programming concepts to solve a real-world-like optimization scenario. Stick around as we break it down step by step and cover multiple approaches. Let's get started. The problem revolves around a group of people planning to commit crimes, where each crime has specific requirements for the number of participants and provides a certain profit. The group has two main constraints: the maximum number of people available for committing crimes and a minimum profit target they want to achieve overall. Your task is to determine how many different ways the group can accomplish at least the minimum required profit while ensuring they do not exceed the maximum number of people available. Since the number of ways can grow significantly, the final result should be returned modulo 10 to the power of 9 plus 7. The input consists of four components: n, which specifies the maximum number of people; min profit, the minimum profit threshold; group, an array where each element represents the number of people required to commit a crime; and profit, an array specifying the profit generated from each crime. The output will be an integer indicating the number of valid ways to achieve the goal while respecting the constraints. Let's look at an example to better understand the problem. Suppose we have 5 people available, a minimum profit requirement of 3, and 2 crimes to consider. The group array is 2, 2, meaning each crime requires 2 people, and the profit array is 2, 3, indicating the profits generated by the 2 crimes are 2 and 3, respectively. The task here is to figure out all the possible combinations of these crimes that allow the group to achieve at least 3 in profit, while staying within the limit of 5 available people. For this example, the possible schemes are as follows. First, they could choose to commit only crime 1, which requires 2 people and generates 3 profit. This meets the minimum profit requirement. Alternatively, they could commit both crime 0 and crime 1 together. This combination would require 4 people and yield a total profit of 5, which also satisfies the conditions. Therefore, there are 2 valid schemes in total for this case. Moving on to another example, let's consider a scenario where there are 10 people, a minimum profit requirement of 5, and 3 crimes to evaluate. In this second example, the group array is 2, 3, 5, meaning the 3 crimes require 2, 3, and 5 people, respectively. The profit array is 6, 7, 8, indicating the profits generated are 6, 7, and 8. The group has 10 people and needs at least 5 profit. Here, the possible schemes include committing crime 0 alone, crime 1 alone, or crime 2 alone. Additionally, they could choose to combine different crimes, crimes 0 and 1 together, crimes 0 and 2 together, or crimes 1 and 2 together. Finally, they could commit all 3 crimes together. This gives a total of 7 valid schemes. Now that we've seen some examples, let's consider a few edge cases that may arise. Edge cases to consider include situations where no crimes can be committed, such as when the group array is empty. Another scenario is when all profits are below the required min profit, meaning only combinations of multiple crimes can meet the requirement. Additionally, there may be cases where the total profit from one or more crimes exactly matches the min profit, which must be handled appropriately. If the number of people required for each crime exceeds the total available, no schemes will be valid. Finally, when min profit is 0, every valid combination of crimes counts as a scheme, since there's no profit requirement to meet. These cases highlight the need for careful handling of different input conditions to ensure accuracy in solving the problem. To begin, let's consider the brute force approach. The idea here is fairly straightforward. We generate all possible subsets of crimes, evaluate each subset to see if it meets the constraints of the problem, and then count the valid ones. Specifically, we iterate through all combinations of crimes, calculate the total number of people used and the profit generated for each combination, and finally check whether the combination satisfies the constraints on people and profit. While this approach is intuitive, the major drawback is its inefficiency. The time complexity is exponential, 2 to the power of n, because we have to evaluate all subsets of crimes. This makes it computationally unfeasible for large inputs. The space complexity, though, is linear or constant depending on whether we use recursion or iteration. However, due to its exponential growth, this method quickly becomes impractical as the number of crimes increases. Now let's move on to the optimized dynamic programming approach. This problem has characteristics that make it well-suited for dynamic programming, specifically overlapping subproblems and an optimal substructure. The main idea is to use a 3D DP table to represent the state of the problem. Each state, dp, I, j, k, tracks the number of ways to achieve a profit of k using j people and considering the first I crimes. The recurrence relation captures two choices: either skip the current crime, in which case the state remains unchanged, or include the crime if it is feasible. Including it requires adjusting for the people and profit contributed by the crime. The base case is dp 0, 0, 0 equals 1, which represents the single way to achieve zero profit with zero people by doing nothing. This structure allows us to systematically build solutions for larger subproblems using the results of smaller ones. To implement the dynamic programming approach, we start by initializing a DP table of size n plus 1 x, g plus 1 x, p plus 1, where n is the number of crimes, g is the maximum number of people, and p is the target profit. We then iterate over the list of crimes, updating the DP table based on the recurrence relation. After processing all crimes, the total number of valid schemes is obtained by summing up all dp, n, j, p values for every valid j, representing the number of people used. The time complexity for this approach is O, n asterisk g asterisk p, as we process each crime for all possible people and profit states. The space complexity is O, g asterisk p, since we can optimize the 3D table to 2D by keeping only the previous state. This trade-off makes the approach much more efficient than brute force while remaining manageable in terms of memory usage. There are additional optimizations we can consider to refine this approach further. One key optimization is reducing the memory usage by replacing the 3D DP table with a 2D table. By iterating in reverse, we can simulate the previous state without needing to store it explicitly, reducing the space complexity to O, g asterisk p. Another option, though less reliable, is a greedy approach, which might prioritize crimes based on their profit-to-people ratio. However, this strategy does not guarantee correctness due to the combinatorial constraints of the problem. Ultimately, dynamic programming strikes the right balance. It handles the constraints on people and profit effectively, scales well with input size, and guarantees correctness. While it is more memory-intensive than a greedy approach, using space optimizations ensures we can address this drawback while maintaining efficiency. The breakthrough realization here was that we could significantly reduce memory usage by employing reverse iteration, which allowed us to simulate previous states without storing them in a 3D DP table. This insight provided a crucial optimization, making the solution not only correct but also far more efficient in terms of memory. In conclusion, the chosen approach leverages the strengths of dynamic programming to solve the problem efficiently and effectively, balancing correctness, computational complexity, and feasibility. By carefully designing state transitions and applying space optimizations, we achieve a solution that addresses the problem's constraints while remaining practical for larger inputs. To solve the profitable schemes problem, we need to determine how many ways we can select subsets of crimes such that the total number of people involved does not exceed n, and the total profit meets or exceeds the specified min profit. Each crime has two associated values: the number of people required, given in the group array, and the profit generated, given in the profit array. The goal is to count all valid subsets of crimes that satisfy the constraints. To tackle this, we begin by defining the inputs. We have n, which sets the maximum number of people available, and min profit, which specifies the minimum profit we aim to achieve. The group and profit arrays describe the requirements and gains for each crime. The central idea is to use dynamic programming to efficiently calculate the number of valid subsets without explicitly generating all possible combinations. We define a three-dimensional DP table, where dp, k, p represents the number of ways to select a subset of crimes that uses up to k people and achieves exactly p profit. This table will serve as the foundation for building our solution iteratively. The DP table is initialized to represent the base case. Specifically, we set dp 0, 0 equals 1, which means there is exactly one way to achieve zero profit with zero people, that is, by selecting no crimes at all. All other entries in the table are initially set to 0, as no subsets have been considered yet. Next, we iterate over each crime in the group and profit arrays. For each crime, we extract the number of people required, people, and the profit generated, gain. Using this information, we update the DP table. The update is done in reverse order to ensure that the values from the previous state of the table are not overwritten prematurely. Specifically, we iterate backwards over the available number of people, from n down to people, and over the profits, from min profit down to 0. For each combination of people and profit, we add the number of ways to achieve peak gain profit with k people to the current entry dp k p. This represents the inclusion of the current crime into the subset. By iterating in reverse, we avoid double counting or prematurely modifying the table entries. After processing all the crimes, we calculate the result by summing up all the values in the dp table for dp k min profit, where k ranges from 0 to n. This sum gives the total number of ways to achieve at least min profit using up to n people. The approach ensures that all possible subsets of crimes are considered without directly enumerating them. There are several key insights to highlight here. First, the reverse iteration over the dp table is crucial for preserving the integrity of earlier states. Second, the use of max, 0, peak gain ensures that we do not attempt to access negative profit indices, effectively clamping the profit to 0 when necessary. Third, the base case achieving 0 profit with 0 people is the foundation of this dynamic programming approach. Finally, the DP approach significantly reduces computational complexity compared to a brute force method, as it builds solutions incrementally. Additionally, the group and profit arrays are used to represent the crime-specific data, while the 3D DP table efficiently stores intermediate results to avoid redundant calculations. To analyze the complexity of this approach, we start with the time complexity. The outer loop iterates over all crimes, which is proportional to the length of the group array. For each crime, the inner loops iterate over the number of people, up to n, and over the profit, up to min profit. This gives a total time complexity of O, len, group, asterisk n asterisk min profit. The space complexity is dominated by the DP table, which requires storage proportional to O, n asterisk min profit. Additionally, the group and profit arrays contribute a space complexity of O, len, group. Combining these, the overall space complexity is O, n asterisk min profit plus len, group. Several edge cases must be considered to ensure the algorithm is robust. For instance, if no crimes are available, group is empty, the result is 0 unless min profit is also 0, in which case the empty subset is valid. If n is smaller than the smallest crimes group requirement, it is impossible to form any valid subsets, and the result is 0. Similarly, when all profits are 0 or negative, the algorithm must handle the case where min profit is 0, allowing the empty subset to be counted. Lastly, the algorithm must handle scenarios where n exactly matches the total number of people required for all crimes. The pseudocode implementation begins by initializing the DP table, where each entry is set to 0, except for DP 0, 0 equals 1, which represents the base case. The algorithm then iterates through all crimes, updating the DP table in reverse order. For each crime, the number of people required, people, and the profit generated, gain, are used to update the table. The update rule is straightforward. For each valid combination of people and profit, the current DP entry is incremented by the value from the previous state that corresponds to excluding the current crime. This ensures that all possible subsets are considered in a consistent and efficient manner. Finally, the result is computed by summing up all entries in the DP table corresponding to DP, k, min profit, where k ranges from 0 to n. This sum represents the total number of ways to achieve the desired profit using the available people. By iteratively building the solution and leveraging the efficiency of dynamic programming, the algorithm provides an optimal solution to the problem without resorting to brute force. This solution implements a dynamic programming, DP, approach to solve the profitable schemes problem. First, we initialize a 2D DP table DP where DP, J, K, represents the number of schemes using at most J people and achieving at least K profit. The size of the table is n plus 1 is x, min profit plus 1, to account for all possible combinations of people and profit levels. We begin by setting the base case DP, 0, 0, equals 1, which means there is exactly one way to achieve 0 profit with 0 people. Next, for each crime, represented by G for the group size and P for the profit, we iterate through the DP table in reverse order, from n to G for people, and min profit to 0 for profit. This ensures that the current state doesn't overwrite information needed for calculations. For each valid combination of people and profit, we update dp j k by adding the value from dp jg max 0 kp. The max 0 kp ensures that we do not go below zero profit, as negative profits are not valid. Finally, after processing all crimes, the result is the sum of all dp j min profit values for j ranging from 0 to n modulo 10⁻9 plus 7 to handle large numbers. This approach ensures that all constraints are satisfied, and the use of a modular arithmetic operator prevents overflow. The time complexity is proportional to the product of n, min profit, and the number of crimes, making it efficient for the input size constraints. Here, we start with the implementation of the solution in Java. First, we import the necessary utilities and define the profitable schemes method, which takes 4 parameters: the total number of people available n, the minimum required profit min profit, the group array representing the number of people required for each scheme, and the profit array representing the profit associated with each scheme. We define a constant mod as 1 billion and 7 to handle modulo operations and prevent overflow. Next, we initialize a 2D array dp, where dp j k represents the number of ways to achieve at least k profit using at most j people. To begin, we set dp 0 0 equals 1, which serves as the base case, indicating that there is exactly one way to achieve zero profit with 0 people. Now, we iterate through each scheme, represented by the indices of the group and profit arrays. For each scheme, we extract the required group size g and its associated profit p. Then, we update the dp array in reverse order to ensure that previously calculated values are not overwritten during the iteration. Specifically, we traverse from n down to g for the number of people and from min profit down to 0 for the profit. During this update, we add the number of schemes possible by including the current scheme, considering the profit and group constraints. We also apply the modulo operation to keep values within bounds. Finally, after processing all the schemes, we calculate the total number of profitable schemes that meet or exceed the minimum profit requirement. To do this, we iterate through all possible numbers of people j from 0 to n and sum up the values stored in dp j min profit. This represents all the ways to achieve the required profit using up to j people. The result is then returned as the output of the method. This implementation uses dynamic programming to efficiently calculate the number of profitable schemes while ensuring that the constraints on group size and profit are met. By using a bottom-up approach and modular arithmetic, the solution is both time and space efficient, making it suitable for the problem constraints. Now, let's walk through a basic example where we have 5 workers available, a minimum profit requirement of 3, and 2 crimes that require 2 workers each, generating profits of 2 and 3 respectively. The first step in solving this problem is to initialize a 2D dynamic programming table, or DP table, that will help us track the number of ways to achieve a certain profit with a given number of workers. This table has dimensions, n plus 1 ace x, min profit plus 1, meaning it has 6 rows and 4 columns in this case, since we have 5 workers and want to track profits from 0 to at least 3. Initially, all values in the table are set to 0, except for dp 0 0, which is set to 1. This represents the single way to achieve 0 profit using 0 workers, essentially doing nothing. The table at this stage looks like this: the first row starts with a 1 in the first column, and all other cells are 0. This initialization sets the foundation for our calculations as we start processing the crimes one by one. Next, we process the first crime, which requires 2 workers and generates a profit of 2. To do this, we traverse the DP table from the bottom up to avoid overwriting values that we still need to reference. Specifically, we iterate through the workers available, starting from 5 down to 2, since this crime requires at least 2 workers. For each worker count, we also iterate through the profit levels, from 3 down to 0. The key update here is that we add the value from dp j2 max 0 k2 to dp j k. This accounts for the ways to achieve at least k profit with j workers by including this crime. After processing this first crime, the updated dp table now has some new non-zero values. For example, dp 2 0 becomes 1, representing one way to use 2 workers to achieve 0 profit, and dp 4 0 also becomes 1, as we can use 4 workers to achieve 0 profit through this crime. These updates reflect the inclusion of the first crime in our calculations. Finally, we move on to process the second crime in a similar manner, updating the DP table based on its requirements and profit contribution. Once both crimes are processed, the dynamic programming table will fully reflect all possible combinations of workers and profits that meet the given constraints. At this point, the solution involves summing up all the values in the last column of the DP table, specifically for profits greater than or equal to the minimum required profit. This gives us the total number of ways to organize the workers to achieve at least the target profit. The final output for this example is the sum of these values, representing the total number of profitable schemes possible under the given conditions. To analyze the time complexity of this solution, we begin with the outer loop that iterates over the group and profit arrays. If the length of these arrays is m, this loop will execute m times. Within this outer loop, there are two nested loops. The first nested loop handles the range of available people, iterating from n down to the current group size g. In the worst case, this loop iterates n times. The second nested loop focuses on the range of profit values, iterating from min profit down to 0, contributing up to min profit plus 1 iterations. Combining these, the two nested loops result in a time complexity of O n asterisk min profit for each crime group. Finally, there's a summation step at the end, which iterates over the range of n plus 1, adding a time complexity of O n. When we combine all these steps, the overall time complexity becomes O m asterisk n asterisk min profit plus O n. However, since O n is negligible compared to the dominant term O m asterisk n asterisk min profit, we simplify the total time complexity to O m asterisk n asterisk min profit. Now, shifting to the space complexity, the primary factor here is the dynamic programming table, DP. This table has dimensions of n plus 1 8x, min profit plus 1, which translates to a space complexity of O n plus 1 asterisk, min profit plus 1. For large values of n and min profit, this simplifies to O n asterisk min profit. Any additional space used for variables, such as loop iterators or temporary variables like g and p, is minimal and does not significantly impact the overall space complexity. Thus, the space complexity of the solution is O n asterisk min profit. Comparing this with a brute force approach, the difference in efficiency becomes clear. A brute force method would involve generating all possible subsets of crimes, which for m crimes means evaluating 2 to the power of m subsets. For each subset, calculating the total profit and group size would take O m time, resulting in an overall time complexity of O 2 to the power of m asterisk m. In contrast, the dynamic programming approach avoids this exponential growth by using a state-based approach, reducing the complexity to O m asterisk n asterisk min profit. This makes the dynamic programming solution far more scalable for larger values of m, n, and min profit. Now, let's consider the best and worst case scenarios for this solution. In the best case, when min profit is very small, such as 0, the inner loop for profit runs only once. This simplifies the time complexity to O m asterisk n. On the other hand, in the worst case, when min profit is large, the inner loop runs min profit plus 1 times, leading to the full complexity of O m asterisk n asterisk min profit. From a mathematical standpoint, the time complexity arises from iterating over all combinations of crimes, people, and profit levels, with each state update being a simple arithmetic operation. This confirms the total complexity of O m asterisk n asterisk min profit. As for space complexity, it is directly tied to the size of the dynamic programming table, which is proportional to O n asterisk min profit. When solving the profitable schemes problem, there are several common mistakes to watch out for. First, it's crucial to consider both the profit threshold and the people constraint together. Many solutions fail because they only address one of these constraints, leading to partial correctness or failing under edge cases. Next, a naive recursive approach might seem straightforward, but it can result in exponential time complexity due to overlapping subproblems. To tackle this, always use memoization or dynamic programming to avoid redundant calculations and improve efficiency. Another pitfall is improperly defining base cases in a DP solution. For example, neglecting edge cases like 0 profit or 0 people can lead to index errors or incorrect results. A good practice is initializing values such as dp 0, 0 to 1, which represents one way to achieve 0 profit with 0 people. Lastly, handling large inputs is a critical aspect. If constraints like the number of people or profit are large, inefficient nested loops or redundant calculations can make your solution impractical. Always aim to optimize both time and space complexity to ensure scalability. Another common issue is confusing the order of dimensions in the DP array. For instance, in a multi-dimensional DP table, candidates may misinterpret what DP, I, J represents, which can lead to errors in state transitions or updates. Always document the meaning of each dimension clearly to avoid such mistakes. From an interview perspective, this problem is commonly used to test your ability to design a dynamic programming solution with multiple dimensions, where constraints like people and profit are encoded. Be sure to clearly explain your state variables, transitions, and base cases. Additionally, interviewers may ask about optimizing space complexity. For example, you might need to explain how to reduce a 2D DP table to a 1D table while maintaining correctness, based on the dependencies of the problem. Testing edge cases explicitly is another critical skill. Scenarios like minimum input sizes, zero profit, or cases where all crimes exceed the constraints should always be part of your testing strategy. Finally, when proposing multiple approaches, such as brute force versus DP, it's important to clearly articulate the trade-offs. Discuss the differences in time complexity, space usage, and implementation effort to show a complete understanding. This problem shares similarities with several other well-known dynamic programming problems. For example, LeetCode 416, partition equals subset sum, involves a similar DP structure with subset sum constraints, making it a great practice problem. LeetCode 494, target sum, is another related problem that focuses on finding subsets meeting target constraints, helping you refine your approach to balancing multiple conditions. LeetCode 518, CoinChange 2, emphasizes overlapping subproblem patterns, which are also prevalent in profit maximization problems. And of course, LeetCode 879, profitable schemes, is the problem we're discussing here. Exploring these related problems can deepen your understanding of multi-dimensional DP techniques and give you more tools to tackle variations of this challenge. When considering alternative approaches to solving the profitable schemes problem, each method has its own trade-offs. A brute force approach, where you generate all possible subsets, is simple to implement but becomes infeasible for large inputs due to its 2 to the power of n time complexity. This method is best suited for small test cases or to understand the problem structure. Recursive backtracking with pruning is another option. While still exponential in the worst case, pruning allows you to eliminate unnecessary computations, making it more efficient than raw brute force. This is a useful intermediate step before transitioning to a dynamic programming solution. Speaking of dynamic programming, this is the optimal approach for large inputs. Though it requires more effort to implement, it achieves polynomial time complexity and can be optimized for space, reducing from n*m to O(m) in some cases. Lastly, a greedy approach may be applicable in simplified versions of the problem where constraints are relaxed. While it doesn't always guarantee optimal results, it can work well for specific subproblems where a greedy strategy leads to correctness. Each of these methods has its place, depending on the problem's constraints and the level of optimization required. Great job following along. To wrap up, we reviewed how to solve profitable schemes using dynamic programming, focusing on optimizing both time and space complexities. Remember to practice breaking problems into smaller states for efficient solutions. Thanks for joining, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!